Hello and welcome to our 7th lecture for the course Introduction to Mechanobiology. Over the last two lectures, we have been discussing about properties of ECM networks and the ECM in particular, how ECM regulates cell function through some of the cues like topography or alignment of these fibers, its bulk properties like stiffness, and how chemical, so for example, density of collagen networks can influence its physical properties, or how do we even measure physical properties of ECM networks. So, over the last two lectures we started having some discussion on how to go about quantifying the mechanical properties of biopolymer networks. Okay. And in that regard, in the last class we had some discussion about whether we want to characterize an ECM network as a solid or a liquid. Okay. So, for a simple solid like a spring, right. So, what distinguishes a solid from a liquid is how they respond when a force is applied on them. Okay. So, for a solid you know that as soon as the force is applied you have an instantaneous deformation, and the deformation remains like that till the end or the duration over which the force is applied, and once the force is removed the solid regains its original undeformed configuration. Okay. However, in terms of tracking how it deforms or what is the relationship between the stress and the strain, we come about by saying a material can be linearly elastic or non-linearly elastic. So, what do we mean by that? So, in a stress strain curve, okay, in a stress strain curve, if this is strain epsilon, which is defined by the extension by the original length, and this is my stress, which is defined as force per unit area. So, if the slope of this line, so if your stress versus strain is linear, okay, then this slope is the Young's modulus of elasticity of this solid. However, if a curve looks like this, then this is nonlinear elasticity, okay, where your slope keeps on changing. So, in comparison to a solid which regains its original configuration instantaneously after the force is removed, in case of a liquid, so when you exert any force it continues to flow, number one, and after you have removed the force it does not go back to its original configuration. So, for a liquid we know that, so the equation, so this the way I have drawn it here, this is for under tension, for when a solid is under tension or compression. Okay. So, E corresponds to the Young's modulus of elasticity. So, I can write a similar equation of tau is equal to G gamma, where in this case tau is the shear stress that is applied. Okay. So, shear stress is applied in a tangential direction, okay, and gamma is the shear strain and G is the shear modulus. Okay. So, in the last class I also told you that for an incompressible material your E I can write it simply as 3G. Okay. So, they are related. So, coming to the question of whether a biopolymer network is a solid or a liquid, so it actually exhibits some characteristics of solids and liquids, and hence the term is used as viscoelastic. Okay. So, for viscoelastic, so when you apply the force there is some instantaneous response which accounts for the elastic component of the behavior, and then some time dependent response which accounts for the viscous component of the force. Now, when we talk about deformation, when any network is exposed to any kind of forces, it can deform in two ways. One in which the volume can change, okay, and one in which the shape can change. So, for most biopolymer networks at the macromolecular level, that means at the micron scale or hundreds of microns range, the volume does not change. This is not true at the micro scale. So, you can define a macro rheology and a micro rheology. So, at the macro scale, the volume does not change, because most of these networks are hydrated. Okay. However, the shape does change. Okay. So, just to re-emphasize, so for elasticity, for tracking elastic behavior, we have the expression tau is equal to G gamma. Okay. So, gamma is the shear strain, tau is the shear stress, G is the shear modulus of elasticity. Okay. For a liquid, you have the equation Newton's law of viscosity, which says that tau is equal to mu gamma dot. So, it is not the shear, but the dependence is on shear rate, okay, and mu is the coefficient of viscosity. Okay. So, now imagine if I were to consider a elastic entity as a liquid. Okay. So, if I apply a constant stress, okay, if I apply a constant stress, so let me write. Okay. So, if I apply a constant stress, I know tau is equal to G gamma. So, if tau is constant, gamma is also constant. Okay. So, this would mean if gamma is constant, then gamma dot is 0. Okay. So, if I were to consider this equation, tau is equal to mu gamma dot. So, if I were to consider a solid as a fluid, okay, so because gamma dot is 0, this amounts to saying mu is infinite. Okay. So, that is to say that ideal elastic materials have infinite viscosity. Okay. And this is the reason why when we do viscosity measurements, okay, or probe the rheology of systems under constant shear, it is not of relevance, because if the material is elastic, this is infinite. Secondly, if you have fragile materials like ECM networks, if you expose them to constant shear, okay, they will actually fall apart. Then the point of actually characterizing their physical properties no more exists. For this reason, what is ideal is to use oscillatory measurements. Okay. So, as written here, and I briefly touched upon this thing yesterday. So, for oscillatory measurements, my gamma is not constant, but it is a sine curve. So, you have gamma naught is the amplitude, and then you have a sine curve on it with frequency omega. Okay. So, the correspondent so if for the material to be viscoelastic, your sigma of t has this dependence where there is a phase shift. So, what is a phase shift? So, if I were to draw, if this is my and this is my strain. Okay. So, okay. So, this would be my stress profile, and this delay is nothing but delta. Okay. So, there is a phase shift of delta. So, if a material was perfectly elastic, then delta is 0. If the material is perfectly fluid, then delta has some value. Okay. So, I can break down this particular expression to write and expand it and write sigma of t, so overall stress, as gamma naught into G prime sin omega t. So, this component is in phase with the strain field. Okay. You have gamma naught sin omega t, and this is gamma naught G prime sin omega t, and plus G double prime cos omega t. Okay. So, because for a fluid, when you expose it to stress, it flows, but it does not recover. So, that is lost, that energy which is pumped into making the fluid flow is lost. This is why this G double prime is referred to as a loss modulus. It is actually the loss shear modulus, because you are measuring shear experiments. Okay. And G prime is the storage shear modulus. So, for doing oscillatory experiments, we make use of a rheometer. Okay. And again, in last class we had discussed that for a rheometer you can have a cone and pleat geometry, in which the bottom plate is stationary, it is fixed, and there is a top plate which has a conical morphology at the bottom, which is in contact with the sample, and this keeps on rotating. Okay. So, you actually position the sample between the top moving part and the bottom stationary part. Okay. So, instead of a cone plate rheometer, you can also have another geometry which is a parallel plate rheometer. In this case, instead of having this conical geometry, the top will also have a geometry like this, but it will rotate. Okay. So, you can have a cone and plate rheometer, but a conical plate as well as a parallel plate rheometer. Now, a cone and plate rheometer makes sure that the entire top surface of the sample is exposed to the same strain, which is not true for a parallel plate rheometer, where the strain at the center of the sample is 0 and the strain is maximum at the edge. This is one reason why cone plate rheometer is preferred. Okay. So, for measuring G prime or G double prime, what is actually tracked is the angular position of this. So, you have some reference point which as it rotates you track its angular position. Okay. The second thing that you can track is the torque that is being applied for rotating the sample at that given frequency. You can do two different types of experiments with a rheometer, one of which is called a controlled rate experiment, and the idea is that you rotate it at a given frequency and you track how much torque is required to maintain that frequency. Okay. So, in a sense you are controlling the strain you are imposing on the sample. Parallelly, there can be another mode of operation called a controlled stress operation, in which you actually control the amount of torque you are imposing on the sample, and what you track is how much strain does it impose on the sample. Okay. So, let us briefly go through some of the measurements that you can measure using a rheometer. So, the obvious simplest case is a stress strain relationship if your material is elastic. Okay. So, in this case this experiment, so for elastic material you can do this in using either the controlled rate case or using a controlled stress experiment. So, you can do it in both ways, and I have drawn two curves here, one a blue one where stress is constant independent of the strain. This is what you will observe. So, the slope of the line, the slope of the line would give you the modulus. Okay. So, what you see, this is what you would observe for a linear elastic material. Okay. So, no matter how much strain you have, it always responds in the same way. The other case is this curve, which gives you a non-linear elastic behavior. Okay. So, the slope of the curve keeps on changing. Now, one thing you can also do, one type of experiment is called a stress relaxation type of experiment, where your input is the strain. So, at a certain point you impose a given amount of strain and you keep it constant for some extended duration, and you see how the system responds. So, these stress relaxation experiments are performed for viscoelastic samples. Okay. So, what you will observe is, in terms of stress, there is an immediate response, but then slowly the stress will keep coming down. Okay. Why does the stress keep coming down? Because this suggests, this is indicative of internal rearrangements of the network or relaxation of the network, hence the term stress relaxation. So, you can have two cases. Okay. So, again I have drawn it in two ways, in which the blue curve, where it drops, but it saturates to some value, while the red curve it drops to complete 0. Okay. So, this is what you will observe, the red curve is what you will observe for a viscoelastic fluid. Okay. At the end this will plateau to 0. However, if it plateaus to some finite value, as is the case in this blue curve, this is called a, so at the end you are observing the behavior of a viscoelastic solid. So, you have, this is the equilibrium modulus of this network. Okay. This is the equilibrium modulus of this network. You can do another, so this is a case where you had kept your strain high. So, you impose a deformation very fast, that is why it was increasing, and then you maintained that level of strain. You can do another set of experiments where you expose it to a force. Okay. So, expose it to a certain amount of force for a constant amount of time and see how the system responds to it. So, these kind of experiments are called creep experiments, and these are important for tracking properties of those kind of tissues which are under constant stress. For example, bones in our body are under constant compression. okay. Or even you can have blood pressure is one case where the blood vasculature is continuously exposed to blood pressure, okay, blood flow, and because of that there is a pressure. Okay. So, for doing these experiments you expose the specimen to a stress, constant stress for a extended duration of time, and during that time you track how does the strain evolve. So, what you find in the strain response is, as soon as you impose the stress, there is the strain, there is an instantaneous strain, and this accounts for the elastic component of the behavior. Okay. So, strain is instantaneous, and then there is an approximate linear increase in the strain till it reaches a maximum. Okay. So, this portion of the curve, so the first two portions of the curve is called the creep. The next two portion of the curve means after you drop, after the stress again drops to 0, what you get is a similar response, but it is in the opposite direction. There is an instantaneous drop in the strain again. Why? Because this is relaxation of the elastic component of the network, and then there is another drop, but this does not drop to 0, it drops to some value. So, if it drops to some value, means this part is the non-recoverable part of the response. So, this is attributed to plastic flows. You can also do another set of experiments which are called frequency sweep. This is very common, and this is what enables you to track how the collagen networks would evolve as time progresses, and it is exposed to stresses of a certain kind for a certain length of time or at a certain rate. Okay. So, in this case I have plotted G prime and G double prime as a function of frequency. So, the frequency actually is varied in log scale. In other words, you can do 0.001, 0.01, 0.1, 1, 10, 100, so on and so forth. Okay. So, for large durations or large frequency ranges, and you track what is the behavior of the network. So, there is one thing that you observe. So, G double prime, the blue curve, is actually above the red curve for a certain frequency range. Okay. So, initially the network is more viscous in nature, okay, but if you keep, so this is the, so where the viscous component or the loss component is more prominent over the storage component, and here because you are deforming the network very slowly. So, okay, so you are deforming the network very slowly, you can have these internal arrangements and the system relaxes. But as you increase, if you start deforming at a much higher frequency, then what you see is G prime increases, okay, and eventually G prime will also saturate. So, G prime increases because the system does not have enough time to relax. Okay. So, this crossover point corresponds to the time scale of relaxation of the network. Okay. So, this is what this is what most ECM networks will exhibit, this like hyaluronic acid will exhibit this kind of behavior. You might also be interested in tracking how a system behaves while it gels or in the presence of some enzyme. So, what you can do is you can do a time sweep where the strain and the amplitude is kept constant, and you monitor G prime and G double prime as a function of time. So, once again here what you see is G prime. So, if let us say a gel is polymerizing, its G prime will increase with time and then saturate, while G double prime. So, you start off with a very viscous material which then polymerizes and forms filaments. So, maximum G double prime is at the initial time point, and then it drops as the network becomes more and more polymerized. For probing the behavior of networks like non-Newtonian networks, what you can do, you can track the viscosity as a function of shear rate. So, this is an example where the viscosity is constant of a certain value of shear rate and then drops. Okay. So, this kind of fluid is called a shear thinning fluid. So, for okay, so you have gamma dot, you have mu or the viscosity. So, you might have three different responses. So, this is a Newtonian fluid, because when mu is constant, it does not exhibit any dependence on gamma dot, you call a Newtonian fluid. So, both of these other fluids are non-Newtonian. So, this is called a shear thinning fluid. This is called a shear thickening fluid. Okay. So, where the viscosity changes over time. So, to summarize, so the number of experiments you can do is quite large. You can do stress strain curves, you can do stress relaxation experiments, you can do creep experiments, you can do creep recovery kind of experiments, frequency sweep. You can also do something called amplitude sweep. So, in frequency sweep, your frequency f changes while you track g prime and g double prime. You can do the same thing in an amplitude sweep, where you keep the frequency constant and you monitor g prime and g double prime as a function of the amount of strain that you impose. Okay. So, a typical case of an amplitude sweep okay. So, here you have gamma. Okay. So, you might have a behavior like this. Okay. So, this let us say is g prime, and what you see, let us say I can also plot g double prime on this curve. No, actually, sorry. Okay. So, this is g prime and this is g double prime. So, this kind of a curve is called an amplitude sweep, and what you see here is beyond a certain strain your g prime decreases. So, g prime is constant in this particular case, and beyond a certain strain it starts to decrease, versus g double prime, which was much lower than g prime, increases beyond a certain value. Why must this happen, or how can this happen? This suggests that beyond a certain strain your network is starting to fall apart, okay, as a consequence of which your g prime value is decreasing and the material is getting more and more viscous, because of which d double prime is increasing. Okay. So, this experiment is called an amplitude sweep experiment. Okay. So, you can have amplitude sweep, you can have time sweep, right. This is used for tracking the gelation kinetics. Okay. And finally, you can do rate dependent viscosity. Okay. So, if I were to summarize, so now in order to do rheology, some points need to be taken into consideration for preparing the sample. So, if you are handling solid tissues like let us say bone, it is easy to, so you should preferably cut them into disc shaped samples. So, the disc should really match the shape and size of the bottom plate. So, it is really anchored properly, okay, of samples 5 to 25 millimeter in diameter, and it can have varying thickness 0.1 to 5 millimeter. Okay. Liquid samples are much more difficult to deal with. So, their height should be limited to 1 millimeter, because if you put more amount of liquid it might flow laterally. So, you do not want to do it. For gelling studies, for example, when you are doing time sweep experiments, the entire gel needs to be initially formed directly between the rheometer plates, and initially without putting the top cone plate cone directly in contact with the gel, so that the gel forms under an unstressed configuration, and then you slowly push the top plate onto the gel. So, for all these cases you have to exert a little bit of compressive force in order to keep this sample in position, and then you can do your experiments. Okay. So, over the last two lectures I had spent considerable amount of time in studying the behavior of collagen networks, right. So, what are some of the experimental observations that we observed? One was the dependence on concentration, right. So, if I have concentration and I am plotting G prime value, I will have values which will scale like this, where G prime roughly scales as concentration cubed. For other biopolymer networks, you might have this G prime will still scale as C to the power x, where x can have any value between 2 and 3. Okay. So, you can also observe a strain stiffening behavior of collagen networks of non-cross-linked or non-cross-linked collagen networks, where G prime values changed. Okay. So, if I plot G prime as a function of strain, okay, beyond a certain strain you have this increase. Okay. And then if you were to do it at the higher concentration, this curve will just shift upwards. Okay. So, this is strain stiffening, and as we discussed in great detail, this kind of strain stiffening behavior is induced by alignment of the individual fibrils in the direction in which you are exerting the force. However, so in these cases, once it aligns with the new direction, the network will not regain its original configuration. So, what you need to do that, to ensure that, is to actually cross-link the network. So, you will have deformation, and then that deformation will be released. When you relax the network, it will go back to its original configuration. Now, one thing is, why do we need nonlinear stiffening? What is the practical relevance of this nonlinear stiffening of these networks? The point is, in tissues, when they are subjected to forces, what this does is, as the network becomes stiff and stiff, that means that for the cell also it is difficult to deform. So, this is a normal process which ensures that the tissue does not get damaged as a consequence of loading, but it regains its original coefficient. Okay. So, nonlinear stiffening really protects against damage. With that, I stop this lecture. In the next class, we will see how nonlinear stiffening can also be encoded at the level of a single protein. Thank you for your attention.